Hi, welcome to the part 2 of integration by parts. Okay, so we are going to talk about how to decide what uh, function to select as the variable u. Recall that to apply integration by parts, we have to decide what is u and what is dv. Now, one of the strategies is to use this acronym LIATE. Okay, what does that mean? L stands for logarithms. Examples are log x, ln x. I stands for inverse trigonometric functions. A stands for algebraic functions. Examples of algebraic functions are polynomials, x cubes, things like that. Then T stands for trigonometric functions. And finally, E stands for exponential functions. Examples are ex and e to the power, let's say, 2x. Now, in your integral, look for functions and out of them, try to assign each function one of these forms, whether it is a logarithm, inverse trigonometric, algebraic, trigonometric, or exponential. And pick the first type as the variable u. For an example, if you have a logarithmic function and an exponential function, your logarithmic function will be the variable u and everything else will be dv. Okay, so let's look at an example 2.2.4. Now, it's not a product of two things, it's a quotient of two things, but I can rewrite it as a product of two functions. 1 over x cubed becomes x to the negative 3 ln x dx. Now, x to the negative 3 can be thought as an algebraic function, ln x as logarithmic function. Now, we have logarithmic and algebraic. So, the first type is logarithmic. Therefore, we are going to choose logarithmic function as our variable u. So, what I am going to do is I am going to assign u equals x to the negative 3. Sorry, u equals ln x. Now everything else is dv. dv is x to the negative 3 dx. Now as soon as we decide what u and dv are, next step is find du, which is 1 over x dx, derivative of ln x, and find v. Integral of x to the negative 3 using the power rule, it's x to the negative 2 over negative 2. Now to apply integration by parts, we are multiplying in this order, u and v, then v and du. So the integral is uv ln x times x to the negative 2 over negative 2 minus integral of v du, x to the negative 2 over negative 2 times 1 over x dx. Okay, now let me rewrite this. Negative half x to the negative 2 ln x, the first term. The second term, we have two negatives, which makes it positive. Half, take the constant out, and when you simplify the terms inside, you get x to the negative 3. Now we know how to integrate that. X to the negative 3. We already did it here. So this is x to the negative 2 over negative 2. So that's the answer. If you want to rearrange things a little bit, you get half x to the negative 2 ln x. That's the first term. Minus 1/4, because there are two 2's and a negative, x to the negative 2 plus c, arbitrary constant. Okay. Now again, the special thing about integration by parts is, given one integral, we are going to rewrite it using another integral. And the hope is this new integral is easier to evaluate than the previous one. Okay. Now let's do few more examples. Let's move to example 2.2.5. Now there are two functions. X, it's an algebraic function. E to the negative x is an exponential function. Now let me write down the acronym LIATE. So we have algebraic and exponential. So the first type to appear is algebraic. Therefore, I am going to choose u equals the algebraic function, which is x. Everything else is dv, e negative x dx. Okay. Right. Now we have decided what is u. The next step is to differentiate and find du, which is dx. Good. We have what is dv, then we can integrate that to calculate v. Integral of e to the negative x is e to the negative x over negative 1. Now to apply integration by parts, I need to multiply uv and v du. So let's apply that. X times e to the negative x over negative 1, that's uv, minus the integral of v du. Let me rewrite this. Negative 1 just becomes negative x e to the negative x. Two negatives, this is positive, integral e to the negative x dx. Now, we were given a complicated integral initially. Now it became much easier to evaluate. And you have to keep in mind, initially it was a definite integral. So we have to evaluate at 0 and 1. Okay, let's evaluate it. When you plug 1, you get negative e to the negative 1. When you plug 0, you get 0, that's from the first term, plus, now the integral of e to the negative x is again e to the negative x over negative 1, evaluated at 0 and 1. Right? So now the first term is negative e to the negative 1 plus, when you evaluate, you get again negative e to the negative 1 minus, when you plug 0, you get 1 over negative 1. So it's just a negative 1. Combine like terms and you should get negative 2 e to the negative 1 plus 1. Okay. Now again, what we did was first decide what to choose as u and v, then apply integration by parts. And here it was a definite integral, meaning you have upper and lower limits. Therefore, we have to evaluate at that value. So you get a number as the answer. Okay, let's move to the next example, 2.2.6. Okay, here we have to evaluate the integral of ln x. It seems like it's just a single function. It's not a product of two things. In fact, we can think it as 1 times ln x. So we rewrote it as a product of two things. One is just a polynomial. You can think it as an algebraic term. Ln x is a logarithmic term. Now, remember, we are looking at LIATE. So L comes first. Therefore, I'm going to choose the variable u to be the logarithmic function ln x. Everything else, dv is 1 dx. So just dx. Okay, so we have decided what u will be and what dv will be. Then we can find the derivative of u. Derivative of ln x is 1 over x dx. Integral of v, integral of dx is just x. To apply integration by parts, you cross multiply like that. So the integral is uv ln x times x minus the integral of v du. Okay, so let me rearrange the first term, x ln x minus the integral of, this simplifies to 1. So the integral of 1 is just x. So it is x ln x minus x plus an arbitrary constant. Now, here we learned a new trick. If you have an integral where we do not know to evaluate the function, and if it is just a single function, we can try to rewrite it as a product of two things, where one factor is the number 1, the second factor is the function. Right? So let's try that on the next example, 2.2.7. Now here you have a single function, arctan or inverse tan. So I'm going to do exactly the same as what I did in the previous example. So it is 1 times arctan or inverse tan x. So 1 is an algebraic term. Inverse tan is an inverse trigonometric. LIATE, so I comes first. Therefore, I'm going to choose U to be inverse tan x, dV to be dx. The derivative of inverse tan is 1 over 1 plus x squared dx. Integral of dx is just x. We have to multiply to obtain integral by parts. It's uv inverse tan x times x minus the integral of v du x times 1 over 1 plus x squared dx. And this is a definite integral, so we have to evaluate at 0 and 1, 0, 1. Right. So let's evaluate the first term. When you plug 1, you get inverse tan 1. When you evaluate at 0, you get 0 minus the integral 0 to 1 x over 1 plus x squared dx. Okay, so now we have to deal with this integral. So initially we were given arctan x. Now it is transformed into x over 1 plus x squared. Okay, so we know how to deal with this using u substitutions. Now I'm not going to show how to apply u substitution here, but after applying it, you will get ln of the denominator 1 plus x squared times a half. So I suggest you to try this. Try t equals 1 plus x squared, a substitution like this. Using that substitution, you can find the integral is half ln 1 plus x squared. We have to evaluate at 0 and 1. Okay, inverse tan 1, the angle where tangent becomes 1 is pi over 4. When you evaluate at 1, you get half ln 2, then minus, because of 2 minuses it becomes plus, and half ln 1. Now, ln 1 is 0. Therefore, we are left with pi over 4 minus half ln 2. Since it is a definite integral, you get a number as your answer. So we have let's go to the next example in the next page. Now this is an example where you will have to use integration part multiple times. So now we realize that we can use LIATE to find decide what u is, but sometimes this will not work. Sometimes, in some cases, some situations, we will have to use integration by parts multiple times. And in some cases, in some situations, we will have to slightly modify it using a U substitution. We will have to use a U substitution before we apply integration by parts. Before applying integration by parts. Okay, so let's look at few examples from here. Example 2.2.8, we have an algebraic function and a trigonometric function. LIATE, so algebraic functions comes first. So I'm going to choose u to be x squared, dv to be sine x dx. Differentiate, du is 2x dx and v is, the integral of sine is negative cosine. Applying integration by parts, x squared times negative cosine x minus the integral of v du negative cosine x times 2x dx. I can rewrite this as negative x squared cosine x plus 2 integral of, I can take negative 2 as a constant, so it becomes plus 2 here, x cosine x dx. Now, initially you had x squared sine x. Now, the new integral is x cosine x, which looks little bit nicer. But to deal with x cosine x, we will have to apply integration by parts again. So, sorry. X is an algebraic term. Cosine x is a trigonometric term. So, I'm going to choose u equals x and dv equals cosine x dx. Okay, if u equals x, du is dx, dv equals cosine x dx. By integrating, you get sine x. Integral of cosine x is sine x. Apply integration by parts. We get, okay, we still have the same thing in the front as the first term. Now the new integral becomes uv x sine x minus v du, integral sine x dx. Now at this point, the last integral is integral of sine x, which is a much nicer integral. Okay, we know the value of integral of sine x, which is negative cosine x. So the final answer is negative x squared cosine x plus, I'm going to distribute this 2, so 2x sine x, and the last one is minus 2 cosine x plus c. All right. So let me stop here for this video, and in next video we will continue from example 2.2.9.